Yes. All right. Okay. Who took my chalk? Who took the chalk? I need the chalk back. Someone came down here and took the chalk. Give me the chalk. Who took the chalk? I can't start until I have the chalk.
Did you have the camera on?
Oh, there's the chalk.
Yeah, blame us.
Who put the chalk on the floor?
Probably you.
I did not put the chalk on the floor. I'm tired, but not that tired. Okay. Is Josiah here?
Yes.
Where are you? Josiah, what are we going to talk about today? Did you do the pre-lecture reading? Oh, Josiah did not do the pre-lecture reading. Everybody say, bad, Josiah. Now, why is that funny?
There's no reading.
I know. I'm just checking. One day I'm going to come in here like 5 Okay. So, so far, I know we've had quite a break, so I'm going to do a little bit of a recap of some of the essential things that we've talked about and developed as a segue into what we're going to talk about today. So to remind you of a few important things, let me first review the three free Lagrangians that we have developed and talked about. We've used two of them rather extensively, and today we'll use the last one. So there's the Lagrangian for a free spin zero particle. There's the Lagrangian for a spin a half particle, also called the Dirac Lagrangian. And then the Lagrangian for a massive spin one particle. Of course, all of these you can turn into the Lagrangians for massless particles just by setting the second term to 0. So you're not restricted to just massive particles when you write these. So we have Klein-Gordon, Dirac, and Proca. And all of these you have proven at some level in your homework, and we've talked about in class. All of these actually imply the Klein-Gordon equation, and the relevance of the Klein-Gordon equation is, of course, that it is actually just enforcing the mass shell condition. That is that E squared over P squared, not E squared over P squared, E squared over C squared minus P squared is equal to M squared C squared, okay, which you can also identify as minus the square of the 4 momentum. Okay. So we developed these three free Lagrangians, and these, of course, describe for us matter, because all matter in the standard model is described by spin a half particles, or it's a spin a half particles, so it's described by the Dirac Lagrangian. The free Dirac Lagrangian, if there's no interaction. Spin one particles, or what will eventually be the gauge fields, are described by the Proca Lagrangian. We haven't yet seen what we're going to do with the spin zero Lagrangian, but we'll talk about that today. After we got these three free Lagrangians down, we then introduced interactions. Via the principle of local gauge invariance. And to do that, we said in the Dirac Lagrangian, okay, we start with matter. So we start with spin a half fields, for example, like the electron or a quark. And in that spin a half Lagrangian, we set it up so that there was some global symmetry, which we then promoted to a local symmetry by replacing the derivative with a new derivative operator we call the covariant derivative, capital D mu, which is defined in terms of the old derivative plus some term which which got a little bit more complicated as we went. Okay, when we first did electromagnetism, everything was kind of really simple, and then when we talked about QCD, it got a little more complicated, and of course, in the electroweak interactions got way complicated. But anyway, this new derivative term is what is required in order to have the symmetry be a local symmetry of the Lagrangian. And what we notice is that in doing so, we're forced to introduce these gauge fields. And of course, we also learn how those gauge fields transform. We get one gauge field for each generator of the group, and this explains why we have, for example, 1 photon, 8 gluons, and 3 weak bosons, as well as the photon and the electroweak unification. Okay, so we've seen this story now at least 3 different times. Okay, and then the last step in all of this is, if we just take these Lagrangians and we put in these new derivatives, we've got these new gauge fields. We have interactions, but these new gauge fields can't themselves propagate. They don't have kinetic terms. So that's where we go and grab the Lagrangian for the spin 1 fields, and we add that. So to our original Lagrangian, spin 1/2 Lagrangian, with the new derivative, we then add the Proca term, but we're limited to just the first guy, because what did we find out about this particular mass contribution for these spin 1 fields?
It's not gauge invariant.
It's not gauge invariant, okay? So we can't introduce a mass term for the gauge fields, all right? Now we'll come back to that in just a minute, but just to remind you of the rest of the details, we started with the example of electricity and magnetism, where the global symmetry we identified as what we called a U1, okay? And that is basically a 1-by-1 complex matrix, or a complex number in simple terms. And that acted on the fields psi in the Dirac Lagrangian as well as psi bar, just by virtue of the fact that they're complex. Since this is complex, I can imagine multiplying it by a complex number. That just makes sense, okay? However, when we then turned to QCD to describe the strong interactions, we wanted to act with something which was more complicated. In particular, we wanted to act with SU3. That is a 3-by-3 complex matrix. It has to act on something that has 3 components, and of course, we constructed this 3-component color multiplet of quark states. So we can say that an up quark actually is a linear combination of these 3 basis up quark color states, red, blue, and green. And that's what the SU3 matrices act on. And then making that a local symmetry, we get QCD, quantum chromodynamics. And then you all groaned because this was really complicated, but then you came back and I made it worse. Because then we talked about not the weak interaction, but the electroweak interaction, which is based on an SU2 left cross U1 Y hypercharge symmetry. Okay. And this acts on left-handed doublets. So for example, you can take the electron and the electron neutrino and they pair up into an electroweak doublet. And you can do this with all of the other particles. So the muon and the muon neutrino form a doublet, as do all the quarks. The up and the down quark form a doublet, the charm and the strange, the top and the bottom. And then also these right-handed states. Okay. And then what we found is that the SU2 left acts on the left-handed doublets, whereas the U1 hypercharge acts on the left-handed doublets and the right-handed states. Okay, and the details were just ugly, and I'm not gonna lie, like electroweak unification, and I wish it were pretty, but it's not, it's ugly. Okay. All right, so that essentially got us through the 3 forces of the Standard Model. And in fact, it pretty much accounts for almost all of the particles that are in the standard model. All of the matter, and remember when I say matter, I mean the things that we're made of. Electrons and quarks and neutrinos and muons and tauons. I mean, we don't see most of that stuff because it decays. Okay, if it's massive and it can decay to something lighter, it will, and it typically does. So our world is largely comprised of up quarks, down quarks, and electrons and electron neutrinos, the lightest states. But nonetheless, all of that stuff is described by this, and then the interactions are based on what you get by enforcing these three symmetries. And in enforcing those three symmetries, you also generate the photon of electromagnetism. Well, actually, we should think of the photon of electromagnetism as coming from this once it's broken. We talked about that last time. And you also generate the W plus, W minus, and the Z naught weak bosons. And then this SU3 gives you the 8 gluons. Okay? So we've got almost all of the standard model. We're, of course, missing one big piece, and that's the Higgs boson. What the hell does it have to do with all of this? And that's what we're going to talk about today. Okay, so, oh, and I should say that just in terms of being complete here, the F mu nu here, we define in general as minus I over G times the commutator of d mu. Okay? And we learned that this is the appropriate way to do it. And the benefit of doing it this way is that you immediately see the more complicated effects that come in when you have a non-abelian symmetry group like SU3 and SU2. In particular, this shows you that the gauge bosons interact with each other, which we showed in detail. Okay? So when you're dealing with a non-abelian symmetry, your F mu nu has to be defined like this. You can't just write the good old d mu, a mu minus d mu, a mu, which we've been used to, since that's not appropriate. All right, are there any questions about this before we move on today? Because if you're not roughly comfortable with this, then there's really no point in going on. All right, good?
Roughly comfortable.
Roughly comfortable?
Very roughly.
Very roughly comfortable? I mean, look, okay, lecture week, yeah, I mean, that sucks. But you should hopefully be at least comfortable with U1, the ins and outs of that. QCD is kind of cute. I will say, you're never going to be comfortable with this. I mean, truthfully, like, first of all, we don't ever work with this because in our present day, we don't see this symmetry. And we're going to talk about that over the next couple of lectures, why we don't see it, where did it go. But we don't actually see this symmetry. The SU2 is broken, or the SU2 cross U1 is broken down to electromagnetism. And what we see is a more complicated picture, which you'll see a glimpse of today, where these things have masses. All of these details we're going to revisit when we start doing calculations. Okay, so it's not ever going to be intuitive, but we will revisit these concepts again and again. Hopefully, it'll maybe get a little more nestled in your brains through calculation.
Are we going to talk more about the violation of the electroweak, the charge conjugation, the parity? And the
yeah, so that's the next topic we're going to turn to after the Higgs mechanism. Is we're going to talk about those discrete symmetries.
Okay.
Okay. Other questions? Sure. Okay. All right. So I left you at the very end of our last lecture on electroweak theory with the following problem. We formulated the electroweak theory by assuming that this was actually a good symmetry. That way we could follow all of the steps that we normally follow when we build a gauge theory. We could just proceed by analogy to the electromagnetic interaction and the strong interaction. But we don't observe this as a good symmetry. Okay? In low energies, room temperature, we don't actually observe this as a good symmetry. So what I'd like to do is flesh that idea out today. But before I get to that, or in the process of getting to that, we actually need to look at two very concrete problems that arose when we looked at the electroweak theory. Okay? The first is, if you recall, the gauge, the mass term for the gauge fields is not gauge invariant. okay, as Jacob reminded us. But the 3 weak bosons are massive. So we have a bit of a conundrum because we really, really like this story, this whole idea that forces come from symmetries. It works so beautifully for electromagnetism and strong interactions. Why does it screw up for the weak interactions? Okay? Is there a way to get around this? Okay? You could just say, screw it. They're massive. I detect that in experiment. I have to put a mass term in here. Therefore, there's no gauge symmetry because this breaks gauge symmetry, and just suck it. Just deal with it. Okay? You could do that, and we're going to kind of do that. We are going to kind of do that in a weird way. But there was another problem, which is maybe a little bit more pervasive. You could just say, well, these are the problem children. You know, if we just kind of ignore them, maybe we can ignore the problem. But there was another issue, and that was if we actually look at the form of a mass term for any of the matter, when we express it in terms of the left and the right Weil spinors, remember that the mass term actually took the following form. And again, this is something that we talked about a little bit more in detail when we talked about the electroweak interaction. We also hinted on it when we talked about Dirac and Weil spinors and looking at solutions of the Dirac equation. But to write down a mass term for fermions, we have to be able to mix the left and the right Weil spinors. Okay? But this presents a problem for this symmetry, because this SU2 left only touches the left portions of these fields. So if we do an SU2 left transformation, I'm only transforming this. I'm not touching that. Well, if you think about how we've been making things symmetric, you know, when we make things symmetric, normally we take the mass term and whatever we do to psi, we do the opposite to psi bar so that the two things cancel. And that's how this is invariant. Well, if I'm only doing something to psi left, there's nothing from psi right that can cancel it. So there's no way in hell that this term can be invariant under something that only acts on the left. So it's not just a problem that the W plus and minus and Z are massive. It's a problem that matter is massive as well. Fortunately, both of these get resolved with the same mechanism. Okay? Just set the masses equal to 0. That's actually what we're going to do. We're going to say that everything is massless. Okay, thanks for suggesting that. Brilliant. Your name must be Peter Davis. Okay, so this is the problem that we're going to talk about. But in the process, we're eventually going to get to an understanding of what it means when I say SU2 left cross U1Y is broken, and what broken means, and what you're left with at the end of it being broken. Okay, so I'm sure I'm erasing a bunch of stuff I'm going to need, but let's just, I'm stupid.
And tired.
Anti-stupid, what did you say?
Considered tired.
Oh, I'm tired, yeah, I'm tired. I'm going to repeat myself several times a day. I'm going to repeat myself several times a day. I might even say the same thing twice in different ways. Okay. So what I'm going to do is I'm going to start by just cranking through a calculation that's going to seem very, very unmotivated. And I'm going to, at the end of it, I'm just going to show you a miraculous result. And then we're going to step back and we're going to look at a picture of what we just did that will make it all more intuitive. Okay? But for now, it's just going to be a calculation. Like, you can follow the steps. I'm not doing anything more than just algebra. Okay? But I promise you that we will, at the end of this, come back to a picture which will help you sort of understand what the hell just happened. But for now, what I want to do is I want to consider a Lagrangian for a scalar field. But I want this to be a complex scalar field. So I'm just going to allow there to be a phi and a phi star. Sorry, let me make this one. It doesn't really matter which one I make complex, but just to be consistent with my notes. So now, the Klein-Gordon equation or the Klein-Gordon-Lagrangian describes scalar fields, and it describes real or complex scalar fields. It doesn't matter. You just, if you have real scalar fields, you just write everything as phi squared. If they're complex, you write it as phi star phi. Okay, but otherwise it's the same Lagrangian. All right. So if we look at this thing, we recognize some familiar stuff. Okay. So that's my spin zero kinetic term. Okay, that's the term that's kind of like the velocity squared. Here, this is actually 4 factors of phi multiplied together. Phi star phi, phi star phi. Okay, so that's actually a quartic self-interaction. Okay? And again, right now this is totally unmotivated. But here's the weird thing. Yes?
I'm just, for coherency, what was this Lagrangian for?
It is just a Lagrangian I'm writing down for shits and giggles right now. Okay? But I'm going to do something awesome with it. Okay? So it is for a spin zero field first and foremost. Okay, so we should be able to recognize some of the features that we know from the Klein-Gordon. So this is for a free Klein-Gordon field. This is just an interaction I could write down. I could write down others. But this term is a little weird. Does anybody notice the peculiarity with this term? And I know, given the way that this class has gone, you're probably just like, yeah, you fucked up.
It has a mu squared in it.
There's a minus sign in it?
It has a minus sign. Okay? I know. You're like, yeah, it's got a minus sign. What's wrong with that for, right? But the thing is right here I wrote, see it? It's there, the ghost of it. Plus 1/2 MC over h bar squared phi squared. The Klein-Gordon-Lagrangian has a plus sign there. So this is actually a wrong sign mass term.
Wait, is that an M? Or is that a mu?
This is a mu.
Okay.
Okay, and we'll talk about, so you could call it a mass if you want, but I
So
don't want to
that's
do
not
that
an
right now
index.
because it's negative.
Wait, it's not an index?
Sorry, this?
Yeah.
No, it's not an index. This is a mu squared. It's a parameter.
Okay.
Yeah, sorry, yeah. Wasn't my choice, it's the standard choice in the literature, so I want you to be able to
It's just
recognize
the
it.
correct wrong sign, not a wrong sign.
Say it again?
It's the correct wrong.
This is a correct wrong sign, yes. Now, there's a lot of people who get really, really hot and heavy and excited about these kinds of things because, after all, the Klein-Gordon equation, as it is usually written, implies this guy, right? But if I take the Klein-Gordon equation and I put in a negative mass squared term, then what I'm really writing is this. I know! But this means that p squared is larger than e squared over c squared. Right? Yeah, I know! But this is gamma mv quantity squared. And this is gamma mc quantity squared over c squared, which is just gamma m squared squared c squared. Square all this, squared, squared.
V is greater than C.
Yeah, this is implying that this thing is moving faster than the speed of light. That's called a tachyon. A lot of people get very excited about tachyons. They go faster than the speed of light. You got a tachyon torpedo? Neither do I. That's the stupidest thing ever. Okay? What we're going to discover is, A, this is not weird. It actually has a very intuitive interpretation. The only reason why people get excited about it is because they keep getting in their head that they're doing particle physics. And in interpreting this as a particle, yeah, you get this weird result, but we're not doing particle physics. Secretly, we're really doing field theory. And in field theory, this has a much more mundane explanation, but a very important one, okay? So we will come back to that when I sort of come back to the pictorial representation of what I'm going to talk about. But for now, let's just take this thing as given. All right? And what I want to do is I want to basically just break it up into two hunks. I'm going to call this, for lack of a better name, T, the kinetic energy. And I'm going to call this whole piece something like a potential. Okay, and it only depends on phi star and phi. Right? Now you might say, well, you shouldn't include the mass term in the potential. That's part of the kinetic energy. I don't know what the hell this is right now, so I'm just going to call it that hunk of the Lagrangian. Yes?
Are you including the minus sign inside the potential?
Yeah, the minus sign is part of this. So this whole U is minus this plus this. Yes. Okay? All right. Yeah. Okay, so guess what we can do since phi is complex? Guess what we can do? I forgot to put my belt on. My pants on. Guess what we can do? Phi is complex. You can.
Conjugate.
You can what?
Make two equations, a real number.
Yeah, you can do that. But what else can you do in the spirit of what we've done in the last few lectures? Starts with the T and rhymes with transform it.
Transform.
Yeah, you can transform it. Awesome. So notice we have invariance under a transformation where phi gets rotated by e to the I theta phi. Okay. When I did this in the case of U1 electromagnetism, I called this e to the I phi, but I don't want to put e to the I phi acting on phi because that would be confusing. And in addition to the fact that that would be confusing, it would be confusing. So, and then phi star naturally would transform as e to the minus I theta phi star. And we can just look at the form of this and say, yeah, that's invariant. What?
Is there a reason you don't have a parameter in there? Or is that?
Theta is the parameter.
It is, okay. Yeah, I'm just a little confused.
So this is a one parameter transformation. We're not doing SU3 or SU2 or anything. So I literally just can specify one number, and that tells me the amount of transformation.
Right, so before you had like a constant, and then you had parameter. Is that what you had before for like, because you had like Q for the...
Oh, yeah. Yeah, strong observation. Good work. In this discussion, I'm actually going to absorb the constant into the gauge covariant derivative. So the story will still work out, but you're right. I'm looking at a slightly different way of formulating this. So the constant that used to be here when we did electromagnetism is now going to appear somewhere else. It's just a constant. I mean, you can keep track of it pretty easily. Okay. All right. So does everybody see that this is a symmetry of this Lagrangian? Okay. Because now, if we consider making this local, that is, we let theta depend on x, okay, and similarly let the transformation act on phi star, then we know we have the usual problem because the derivative acting on phi is going to act on the exponential because the parameter has spatial dependence, or space-time dependence. And so the invariance of the original Lagrangian under the global transformation is not going to be preserved under the local form. Okay? So we do what we normally do. We fix it with a new derivative. Now the derivative in this case is going to look a little different than it did last time because of exactly what you pointed out. The parameters that I used to put here are now going to come into the derivative itself. Okay, so I'm going to have a covariant derivative, which is just the old partial derivative plus something times a new thing that we will eventually recognize as a gauge field. Okay? And then we allow this new gauge field, A mu, to propagate by adding in a kinetic term for it. So again, I'm just repeating the steps we've done now. This is the fourth time. I told you I'd be repeating myself today. With a factor of 1/16 pi, f mu nu, f mu nu. And since in this case, our transformation is just multiplication by a complex number, that's just u1, this time the f mu nu is the simple one. Okay. All right. So at the end of the day, I get a Lagrangian that looks like this. Okay, so that is what I get at the end of making this U1 a local symmetry with the usual recipe and adding in a kinetic term for A, et cetera, et cetera. Okay? And again, it's pretty much what I started with. The only difference is I have a new derivative and I added in the plus 1/16 f mu nu. Yes?
So when did you conjugate the d mu in the first one? Because the conjugation sign, is that on the phi or is it on d mu phi?
Oh yeah. So that's a good question. So here I don't have to conjugate d mu because d mu is a real operator. Remember, the Lagrangian needs to be a scalar, a real scalar. So here I don't need to conjugate this, but when d mu becomes itself complex, then you can move that outside, conjugate the whole thing. Yeah, that's a good question. Okay. All right. So far, this is not very interesting. But now we're going to say something interesting. If I asked you what this described, you would say, well, it's a locally U1 invariant theory of a complex scalar field, which is tachyonic and is interacting with itself in this funny way. That might not seem like it gets you very much, but it's time now to take a step back and say, well, what do we do when we do particle physics? What does it mean to do particle physics? And this is actually something which we're going to revisit extensively when we start doing calculations, because this is the very essence of what we call perturbation theory. So remember, we're writing down these Lagrangians, and they are in terms of fields. So things like phi are functions over all of space and time. Similarly, the field A is defined over all of space-time. So these are, if you could think of them like surfaces defined throughout space-time. But at the end of the day, what we experience of these fields are usually particle-like fluctuations. So if you think about it, you have this big field everywhere, but a particle is really just a tiny localized fluctuation. Particles are multiples of these, and they're just kind of bumping into each other and interacting in funny ways. Okay, and we have fields stacked on top of fields, so we can have an excitation in one field interact with an excitation in another field. Okay? So the question is if I'm working with a Lagrangian for the whole field, where the hell do I get out these little particle things? Okay? Well, that's actually kind of straightforward, because what we can do is we can take the field phi and we can take some background field configuration. I'll just call it phi naught. Okay, and that might have some space-time dependence. And then we consider a tiny fluctuation above that, okay, where this has some definition of what we mean by smallness, okay, and eventually that'll come into we want certain expansions to converge, et cetera, et cetera. Okay? But for now, we're not too worried about the details. This would describe the whole thing, and this would just describe one of these little bleeps. Okay, so for example, this would have compact support. It would only be non-zero inside of some neighborhood. Outside of the neighborhood, this thing would be 0, or it would actually be, it would be 0, so that you would just have the original field configuration. And similarly for the A nu. Okay, but the question now is, so these are the fluctuations, these are little particles, what do I put in for these? Okay, now most of the time when you do particle physics, when you do calculations in particle physics, almost every time you do a calculation, your beginning assumption is that these are 0. You just take the field to be 0 everywhere, so the only thing that exists are the small fluctuations. Okay? And you can describe a lot of stuff with that. Unfortunately, you're missing a very important part of the standard model. All right? So then the question we might ask is, okay, well, what if I didn't want to take these to be 0? What would I take them to be? What am I allowed to put in for the total field configuration above which I'm considering these small fluctuations? And the answer to that is essentially that we take the Lagrangian for our fields, we find the equations of motion, we solve those classical equations of motion, and the solutions to those equations of motion are what we use for the background fields. Then we allow fluctuations about those backgrounds, and it is these fluctuations that we actually treat quantum mechanically. Okay? So, if we want to find solutions to these equations of motion, what should we be looking at? Well, there's actually a pretty simple method of finding solutions to the equations of motion if you want to restrict yourself to kind of boring configurations. So, if we focus on static solutions, then we're basically saying that we want the field configuration to be constant everywhere. We do not want the background field to be waving around different values at different places. Okay? That is, we want the derivatives of the field to vanish everywhere. But that means you're setting the kinetic term to 0. Now remember, the equations of motion you get by extremizing this action. So if you want to extremize this action under the assumption that the kinetic term is 0, then all you're doing is extremizing the potential. That is, the equations of motion just reduce to the partial of L, partial phi, or sorry, partial U, partial phi is 0. Because if you're going to demand that the kinetic term be 0, the only thing left in the Lagrangian is this potential. So you're just extremizing the potential. Right? Fortunately, we can do that. It's not the worst thing. By the way, these are kinetic terms as well. Okay. So if we extremize this potential, if I want to look for a background field configuration for phi as opposed to phi, yeah.
So are we focusing on setting solutions for both fields, both the gauge field and the actual field that we're interested in?
Well, right now the gauge field itself doesn't have a potential like this. Okay, the gauge field has an interaction with the scalar field by virtue of local gauge symmetry, but I'm setting this whole kinetic term to 0. So if you will, a solution for the gauge field that extremizes this is that the gauge field is 0. Then the kinetic term. So I'm going to write down a whole consistent solution in just a second for both A and phi. But you're right, a solution is a solution for specifying both A and phi together. Okay. So one thing to note, and you might or might not realize this because we only wrote down the Lagrangian and the Klein-Gordon equation for a real scalar field. But that is, if we write down the Klein-Gordon Lagrangian and we want to find the equation of motion for phi, we actually have to be considering the variation of the Lagrangian with respect to phi star. Okay? And if you go back to our derivation of the Dirac equation from the Dirac Lagrangian, you might or might not remember that to get the equation of motion for psi, we had to vary it with respect to psi bar. And to get the equation of motion for psi bar, we varied with respect to psi. Okay? This complex scalar field works the same way. The important point of that is just that if I want an equation of motion for phi, I really need to be considering the derivative with respect to phi star being 0. It doesn't matter if you took the derivative with respect to phi or phi star, you're going to get an answer which is basically the same because phi and phi star enter in the same form. Okay. All right. So if I take this derivative and set it equal to 0, we can write down what we get for that equation. I'm going to stop picking up the wrong sheet. What I find, okay, remember this is my u of phi star and phi. If I take the derivative of that and set it equal to 0, what I find is minus 1/2 mu squared phi plus 1/2 lambda squared phi star phi phi. Okay. And we want to set that equal to 0. All right. If I'm setting this equal to 0, I can just erase all the common factors. This is phi star phi, so I might as well just call that phi complex magnitude squared. So that is the condition I get for extremizing this potential, just that minus 1/2 mu squared plus 1/2 lambda squared phi complex magnitude squared equals 0. Okay? So now let's look at some solutions. So as a first solution, we can set the gauge field equal to 0 everywhere, and we can also set phi equal to 0 everywhere. Okay? Because remember, I erased a phi. So phi equals 0 solves this equation before I erase it. So phi equals 0, which is certainly constant everywhere. Phi equals 0 extremizes this potential with all the kinetic terms being 0. Okay? So this is a full solution to the equations of motion. And then, if I consider fluctuations about these, the field phi becomes the original field, or sorry, the solution that I'm considering, which in this case is 0, plus fluctuations, and the gauge field as well. Okay? Now, what I do at this point is I take these field configurations and I plug them into this Lagrangian, and what I will then have is the Lagrangian that governs these fluctuations. Right now, this seems stupid. You should be going, why did you do that, Flournoy? Because if I take these and I plug them into that Lagrangian everywhere I see these, all I'm going to get is that Lagrangian written with delta phi and delta A everywhere instead of phi and A. So I literally can do this instantly. I just come in this Lagrangian, and everywhere I see A, make it a delta A, and everywhere I see a phi star, make it a delta phi star, and so forth and so on. Okay, it's trivial to do this. It's boring. But that's what you get. So the Lagrangian for the original fields looks identical to the Lagrangian for the small fluctuations if the solutions for the backgrounds you're starting with are 0 everywhere. But that is not the only solution. There's another one we can work with. Okay? After all, if I erase this phi, which I can do because it appears in both terms, there is still a solution to that equation with a non-zero phi. So the second solution I can consider is again to take a mu equal to 0, but this time I can take phi equal to some non-zero constant I will just call phi naught, where phi naught satisfies that phi naught squared equals mu squared over lambda squared. Okay? And you can see that right here. You just move this term to the other side, get rid of my 1/2, move that mu squared up to the other side, and you see that if phi naught magnitude squared satisfies that, then the potential is extra mass. Okay? Remember, in all of this, phi is a complex field, so I can write it, if I want, as that. And similarly, I can write this as phi 1 minus I phi 2. Okay? But now, what we really want to study are the fluctuations. So, what we want to do is we want to take, so let me just take a particular solution. You might notice this is a family of solutions. Okay? Any phi naught, any complex phi naught which satisfies this is going to work. So let me take a particular one. So consider when the real component of phi is mu over lambda, the complex component of phi is 0, and a mu is 0. Okay? This satisfies all of these conditions. A mu is 0, obviously, and if I take the complex magnitude of this, I just get mu squared over lambda squared, because this doesn't contribute. Now what I want to do is take each of these and allow them to fluctuate. And when I write x here, I mean x mu. I'm just getting tired. Okay? Please note, these are constants. They're just the constants that are appearing in the Lagrangian here. They're not fields, they're just numbers. Okay? The things that depend on position are the fluctuations. Now what I'm going to do is I'm going to rename some things. Okay? Because I'm going to write down a very nasty expression, and I want to clean it up as much as I can. So I'm going to call this mu over lambda plus, and I think the symbol I'm going to use is eta. I'm going to call this beta, and I'm going to just call this a mu. Okay? So the fluctuation of the real part of phi, I'm calling eta. The fluctuation of the complex part I'm calling beta, and I'm just going to call the fluctuation of A. That way I don't have to write a bunch of deltas. Okay? Does anybody have a joke? Anybody have a good joke they want to tell? It's like 3 minutes long, because I'm about to write for about 3 minutes.
You're the one about the pencil? Didn't have a point.
Does anybody have a joke? In the sense that it's funny? I'm sorry. Okay, so the Lagrangian for our fluctuations now, so eta, beta, and A, I get, again, this is literally plug and chug. You can't do it all in your head in the moment, but you can do this. I'm literally taking this and I'm plugging it in everywhere I would have a phi 1 in this expression. Of course, it's a phi 1 minus I phi 2 star, etc. I'm just literally plugging it in, okay? And then I'm doing the same with this and the same with this. So into this Lagrangian everything goes, and out pops, after quite a bit of cancellation, there's a ton of terms that cancel, and then rearranging things for better purposes of visualization, something that looks like this. We're going to need some jokes. You guys are really, like, you're sucking on the joke front, I'm not going to lie.
What do you call a dog with no legs? Doesn't matter, because it sure as hell isn't coming.
Hey, do you guys know that protons have mass? I didn't know they were packed.
Why does the chicken coop only have 2 doors? If it had 4, it'd be a chicken sedan.
Pretty good, I like that one.
Guys, what do you call a fish with no eyes?
What did the snail riding on the turtle's back say? Whee!
What did the fish say when he hit a wall?
Dang.
It was brown and sticky.
A stick. You guys are terrible. You should teach physics classes. You're qualified.
Those jokes are probably the worst jokes I've heard.
So 2 whales are sitting on a bar. One whale goes, the other whale goes, go home, Carl, you're drunk.
Those are really good whale sounds.
Those were good whale sounds. So these 2 sausages are in the oven, and one sausage turns to the other sausage and he goes, man, it is hot in here. And the other sausage goes, oh my God, a talking sausage. That's my tired joke.
What did one lawyer say to the other lawyer? We are both lawyers.
You really don't get that? And I want you to know that I'm writing this on the board because I was confirming this at 6 this morning, tired off my ass, and I was like, I'm not going to have a minus sign in there. Because all of this changed when I changed conventions. So you guys should check this. Okay, no more jokes, please. You guys are killing me. All right. That is what you get.
It's after cancellations.
Cool. This is after cancel. I know before cancellation it was ugly. So this is about the ugliest thing that we have seen, and believe it or not, this is a simple example. Okay. But I want to stress to you that all I have done is the following. I took my original Lagrangian. I solved the equations of motion. I got this non-trivial solution where something was not zero. I looked at fluctuations around it. I stuffed all of this back in to find the Lagrangian for the fluctuations. Okay? Does anyone see the miracle?
You didn't make a sign there?
Let's talk about what this describes. Eta is what kind of field?
Scalar.
It's a scalar field. It's a fluctuation of a real scalar. So it's a scalar, but it has the correct mass. What about beta?
It's also a scalar field.
Beta is also a scalar field, which we might expect because it is just a fluctuation of the complex component of a scalar. But it doesn't have a mass. What about the fluctuation A mu? Hey!
Sorry.
What do you observe about A mu?
It's a complex scalar.
It has mass
No.
squared.
What does it have?
It's mass squared. It's charged.
So A mu is hiding in here, but what is this? What is this? It's a bunch of constants times A mu, A mu. You guys just don't get that excited about physics.
I'm just really confused.
Yeah.
I'm super lost.
Look, this is big and complicated. Right now, just ignore the second two lines. I'm just looking at this term, and this term.
Okay.
Okay? So if I look at this term, this is just the Klein-Gordon-Lagrangian for a field scalar beta, and that's the mass. Okay?
Is that like a capital U for the mass figure, or what is it?
This is the Klein-Gordon for a real scalar field beta, but there's no mass. And then this is the Procol-Lagrangian. This is a funny combination of constants, but it's just a constant. So it's something times A mu, which is what the mass term in the Procol-Lagrangian looks like.
Okay, so we're just relating these back to the Procol-Lagrangian equations.
Yeah, okay. And then the second two lines just represents a whole buttload of crazy interactions between them. Okay, I mean, if I look at this term, you know, this is eta with the derivative of beta times A. It's a product of three different fields. It's just an interaction. Every term in here, this is eta cubed. That's an interaction. This is beta squared times zeta. That's an interaction. Okay? Nothing in the second two lines are quadratic. They're all going to be third order or higher. So they're just interactions between fields. Okay? It's the quadratic and the kinetic terms that you want to focus on to sort of identify what you're dealing with. Do you guys realize what we just did? What did we start with? We started with, we didn't start with matter at all. There was no matter. There was a scalar field. And we had a symmetry, and with that symmetry we introduced a gauge field. But as usual, when we introduced that gauge field, that's the kinetic term we gave it. We wouldn't allow it to have mass because the mass broke gauge invariance. And if I stick to trivial solutions to the equations of motion, this is the same Lagrangian I'm going to deal with. I would still have a massless gauge field. But by allowing myself to consider this non-trivial solution as my background, suddenly the gauge field has a mass. It is by virtue of the gauge field coupling to this scalar field phi, and phi having this non-trivial value that makes it appear as if what was a massless gauge field now has mass. Phi is what we call the Higgs field.
Is that first Lagrangian when case one where everything is zero?
Yeah. So this Lagrangian is what everything is based on. So I can take this Lagrangian and I can plug in these solutions,
Yeah.
but since I'm just taking zero, I just replace phi and a everywhere with the fluctuation. So it would look exactly the same. I can take this same Lagrangian, same theory, and instead plug in these solutions, and this is what I get.
Okay.
And what I want you to see is that because of the form of this solution, in particular because of the form of the Higgs field, the massless gauge boson now has a mass. When people say the Higgs boson or the Higgs field is responsible for giving things mass, this is what they mean.
So here we have a massive field, phi, right? And a massive gauge field. Both are massive.
You're talking about here.
Yeah. From,
So eta is massive
Yeah.
and A is massive. Beta is still massless.
okay. So we still have two massive things.
Two massive things.
Yeah.
Yes.
But so why did we assume that a mu is zero? All we care about is it being constant.
Well, unfortunately, if a mu is not zero, then you can't set this to zero if phi is not zero. Right? So the a mu comes in with the derivative. And so assuming that phi is constant means that the derivative of it is zero, but you do also need this product to be zero, even though phi is not zero. So that's why to get a solution, I also have to assume a mu is zero. Is that sure? Okay. Yeah, it's just that the kinetic term is more than just a derivative. It's a derivative plus something times a. And I want that whole kinetic term to be zero.
So we're trying to understand the nature of the fluctuations. So there are different types of fluctuations, right? So are these quantum fluctuations, first of all?
Well, you would, so what do you mean by a quantum fluctuation? What does that word
So I guess
mean?
there's different kinds. You could have like a type of harmonic oscillator effect, like a small type of perturbation like that, or you could have like the Casimir effect, where you have like spontaneous creation of particling and particle.
There's a much deeper story underlying all of this, but the bottom line of it is what we're doing is ultimately we would take this Lagrangian and we would quantize all of these small fluctuations, eta, beta, and a mu. And from that we would get a perturbative manifestation of this quantum field theory. So yes, they're quantum fluctuations in the sense that we would eventually quantize it. Right now, I'm not really quantizing anything. I'm just writing down the Lagrangian for the fluctuations. We're not doing quantum mechanics yet. That's when we're going to start doing calculations with Feynman diagrams. And we're not going to do quantum field theory, but I'll kind of show you where it ends up. But yes, the fluctuations we would quantize. We're not quantizing the background fields themselves. But you might say, why don't you quantize the background fields if you're going to quantize the fluctuations? And this goes into the whole story of interpreting this thing as an effective Lagrangian coming from an effective action versus a fundamental action. And so if you have an effective action, then you can actually just solve the equations of motion for the background fields, and then you can quantize small fluctuations around it. If you know anything about effective actions, that might have made some sense. Wow, hands across America. Let's just start with this side, go across.
So what happened to the tachyonic behavior in that one term? Where
Well,
does that-
you'll notice there's no tachyonic thing here, right? So we got rid of the bad, I've erased all this stuff that I wish I could point to. We got rid of the bad thing, okay? And we got some goodness, we got some love. this is really the love. I mean, that we got now a massive gauge field.
So there was nothing physical at all about that?
Well, we're not going to get to it today, but the picture I'm going to draw is going to make all of this make a lot more sense, and you will also understand the tachyonic part, why that was there, what it actually meant. Mark.
So we started with the Lagrangian for the Higgs Lagrangian, and you're saying that now we're popping out with a massive gauge field, but
Yes.
all we did was impose a gauge invariance on the Higgs Lagrangian. We haven't started coupling this to the other fields.
Sure, yeah, no. Right now I'm looking at the simplest possible case. I'm trying to show you how, with a scalar Higgs field, you can take a massless gauge field and give it a mass. To do this in the standard model is fugly. Because if you think about it, the relevant symmetry that we do this with in the standard model is the SU2 left cross U1Y. I can't even, I don't want to write that. This was bad enough, and this was U1. I do not want to write it down for this. Of course, it's been written down. Remember that Lagrangian I showed you at the beginning of the semester? Moreover, and when I draw the picture, this will make more sense. Pictorially, you can actually visualize U1 transformations because they're just rotations in a circle.
Yeah.
Okay? You can't visualize these. So working with a simple U1 example, it's a toy example, but it's going to let us visualize it, and it's the same basic story that you have to do in the standard model when you want to talk about giving the W plus minus and Z bosons masses.
Is there some reason you sectioned off to the interaction with the end there? Because you have curly brackets around the start of
there's nothing special about the order of these. They don't mean anything. I don't know why I wrote it in this particular way. I was combining, some terms that look, similar and so forth, but no, there's nothing fundamental to it. The key is to recognize these first three terms as kinetic terms with masses. And then the rest of this is just interactions.
Just to bring it back for a second, this is all predicated on the fact that these are static solutions, right?
Yeah.
Okay. So no kinetic solutions.
Right. The fluctuations we allow to vary with position, but the background fields that we're starting with are not fluctuating. So, do you guys have an idea of what I mean by a background field and then a fluctuation? Okay, if I have a lake and I drop a stone in it, I get this little wave. Okay. Now, if I take the lake and I make it really, really hot, and a lot of the lake evaporates, the whole lake goes, and then I can drop a rock in it and I'll get a little fluctuation. Okay, the lake itself is the background, and the whole lake can be here or the whole lake can be here. Those are just different background configurations of the lake. What I want to study though is the little fluctuations that you get maybe by dropping a rock in it. Okay, so most of the time we just take the level of the lake to be 0, and then our fluctuations are above 0. But for this particular example, we're taking the whole lake to be above 0. Okay, yeah.
So when there's no fluctuations, this is a much less interesting story. And with the Higgs
Wait,
field,
when you say there's no fluctuations, or when you're in this situation?
I guess I was thinking when there's no fluctuations. So when you just have the lake and there's no stone.
Well, then you're not talking about the behavior of particles. You're just talking about what we call the vacuum. So that's another. Thank you actually for asking that question, because this is a piece of terminology that I can give you. Another name for these background configurations is the vacuum. That is, what do you have if you take away all the particles? You get a vacuum. The tricky thing is that your original, like in chemistry or wherever the hell you first saw the word vacuum, your idea of vacuum was you take space with matter in it, you suck all the matter out, and what's left is the vacuum. The vacuum is the most empty space you can possibly have. But what I'm arguing to you is that the vacuum can actually be an interesting place. And the Higgs vacuum is an interesting vacuum. It's actually got some non-zero constant field part. And then you put particles in by allowing fluctuations above the vacuum. So if you take away all the fluctuations, you're looking at the vacuum. This vacuum happens to be a non-trivial one.
So besides just the result that we do see things having mass and stuff, is the Higgs field actually measurable? Does that correspond to some kind of real thing?
So, okay, so is the Higgs field measurable? What is this right here?
Massive scalar.
It is a massive scalar, but it is a fluctuation,
Right.
right? It is the fluctuation here, okay? So it would represent a particle that you could go and detect.
Right.
What particle would that be? That's the Higgs boson.
Oh.
This eta is the Higgs boson.
Gotcha.
This is, if you will, in the case of the standard model, and making this the more ugly realistic example, this would be the W plus, the W minus, or the Z, the ones that were massless and then got mass through the Higgs mechanism. I still haven't told you what this is, and we'll have to talk about that next time. Okay, but this, yes, you can experimentally observe this, and they did as of 2012.
But as far as the background in the field, is that observable besides in just the results that you
So, well, no, the background, so the thing is that what you've just learned is that the background determines the behavior of the fluctuations. If I pick one background, the fluctuations behave according to one Lagrangian, but if I choose a different background, then the Lagrangian for the fluctuations changes. So what we observe is the fluctuations.
Okay.
But we can infer from the behavior of the fluctuations what the background might look like.
Okay.
Okay? But no, you don't set up an experiment where you go out and look at the background, you know,
It's
it's
just a mathematical construct that leads to observable results.
well, I don't want to call it a mathematical construct. So there is, okay, so, all right, I should be completely honest with you, and I should say that there is one scenario where the background field configurations have a very, very important observational effect. And that is that the background field configurations, even if they're completely uniform and constant and smooth, they still contribute to the total mass energy of the universe and therefore the curvature of the universe. So when you're doing general relativity and you're studying cosmology, the shape of the universe depends on these background field configurations. It's the only place in physics where they actually matter. Right.
I just kind of wanted to add something to that. This might help as an analogy. Like when you think about a background electromagnetic field, for instance, what do you actually measure in an experiment? You're going to actually measure a photon. And the photon is a boson as well. So that's literally what you're measuring. So you're measuring the boson, which corresponds to the field.
Yeah.
So if you're saying the background kind of impacts what the fluctuations look like, having different backgrounds, is that produces different fluctuations?
Absolutely, yes.
Is that where in one situation it produces an electron and then another produces
No. So the only part of the standard model story where we play this game is with the Higgs field. It is the only field that we give this non-trivial background to. All of the other particles, we just take them to be 0 and then fluctuate around 0. Okay? If you did take non-trivial backgrounds, okay, then you would get some very interesting results. Unfortunately, they're not feasible physically for the following reason. If I take, for example, a vector field, something that has a direction, and I make it constant everywhere, okay, you might say, oh, that's a solution to the equations of motion, and you'd be right. The problem is if I have a non-vanishing vector that's constant everywhere, I have broken Lorentz invariance. There's no rotational invariance because there's a special direction in space-time. Strangely, the same thing happens for a spinor. I can't take a spin-a-half field and give it an everywhere constant value because now there's again a special direction in spin space. The only field I can do that with is a scalar. Because I can give a scalar a non-zero value, but still have rotational invariance, because scalars don't transform under rotations. So you can get some very interesting physics if you do that. And there are scenarios where people do that. Right? But we're just not going to talk about that in this class. People talk about spontaneously broken supersymmetry and so forth, and they give vevs to spinor fields and so forth. But that's a little bit beyond where we're going to go.
So we chose a very specific phi1 to be mu over lambda. What if we chose...
So when I draw the picture next time, that question will be answered very beautifully. It will tell you what all of this means, what it would mean if you chose a different solution. It will give you a reason why this is massive, why this is massless.
Perfect.
Okay? And we'll be able to talk about what happens to this thing in the real world. But all that's going to have to wait till next time.
If you had phi1 and phi2 to be both be some type of constant, that still satisfied it, wouldn't you get both of them to be massive at that point? So both theta and beta to be massive?
If you took...
So if you said phi1 was something,
Yeah, you
phi2
would.
was something.
You would.
So then
you would.
Would that eta still be the Higgs boson at that point?
So
Remarkably unproductive.
so if you took them both to be non-zero, then I'm trying to think of a way of answering this without giving away the punchline.
I can wait till Thursday.
So if I just take like phi1 and phi2 as two axes in the complex plane,
Okay.
the solution that I took here was just a point there.
Oh, yeah.
Where phi2 is 0 and phi1 is non-zero. If I take them both to be non-zero, then I might be considering something like that.
Yeah.
Okay? But I can take that and I can come to an orthogonal solution, and where this one will be massive, this one will be massive.
Okay. I think I see it.
It's, again, it'll be much more intuitive.
I do.
Okay.
So you're talking about how with scalar fields we do that? So if this was the perturbate approach, where with a it's like non-trivial background.
Do a non-trivial background for...
Are like, or gauge field or something. Because
Oh, you do it all the time. I mean, if I have an electric field in space, it's no longer rotation invariant. And if I set up a parallel plate capacitor and there's an electric field that goes from one plate to the other, that is giving the a mu itself a non-trivial background.
I was just wondering, can we construct something similar? Because here we're just talking about like scalar fields, right? So Lagrangian could we just use the Klein-Gordon one works for scalar fields, right?
Yes.
So could we plug in a solution like this and get something different? Because here we use a very specific Lagrangian that you gave us, but could we plug in something like this into the general Klein-Gordon equation and get something meaningful?
When you say, I'm confused what you mean by the general Klein-Gordon equation. The Klein-Gordon equation is just a kinetic and mass term for a scalar field. And then what I've done is I've added in this special, A, I've screwed up the mass term, and B, I added in this particular quartic interaction.
And those two are the only ones that are responsible.
Well, it is this combination of things which gives me that non-trivial solution.
Oh, right. Yeah, the mu over lambda.
Yeah.
Okay.
So, for example, if I had left this term out, there wouldn't be a non-trivial solution that's static. I could still let like everything vary with position,
but there would be
something interesting, but it would be a static solution. What's the name of beta? Say it again. What's the name of beta? It's the Goldstone boson. Okay. How do you spell that? Goldstone. Okay, Goldstone. Yeah, or the Goldstone mode. And we'll talk about that next time. But it actually plays a very important role because there's a part of this story which might have left you puzzled, and that has to do with giving something mass is a it's not a continuous limit. So if I take something that's massive and I take it to be massless, there's discontinuity that happens. You're forgetting about. I taught you about it, but you're forgetting about it. Oh, sorry. No, I was wondering if it actually kind of went up again.
I'm confused by the changing the background changes the fluctuations. So the fluctuations are particles. But you said eta is Higgs boson. So does that mean there's different values of the Higgs boson? That doesn't sound right. I'm kind of confused.
So the Higgs boson, so there's the Higgs field and then there's fluctuations in the Higgs field.
Oh.
The particle,
Right.
the Higgs boson particle is the fluctuation in the Higgs field.
Okay. So by changing, I guess I don't understand sort of how you can get different values of the background.
How you can get different values in the background? Sure. What do you mean how you can get different values?
So if you can have different fluctuations, doesn't that mean you can have essentially several different values for the background?
No. So that's the stipulation is the fluctuations themselves do not change the background. To change the background is a non-perturbative thing. You actually have to change stuff everywhere. Fluctuations are by definition localized in space and time. So when I talk about the Higgs field having this non-zero value, I'm literally taking the Higgs field everywhere in space and time and I'm increasing its value. You can do that with fluctuations, but it requires a coherent state of fluctuations extending throughout space and time. It's not a small phenomenon.
Right.
So the fluctuations are what we call perturbative physics, and the backgrounds are aspects of what we call the non-perturbative physics. And you can't get non-perturbative change by considering perturbative physics only. Okay. So it's again, going back to the lake and dropping rocks in it, you're not going to raise the whole level of the lake by dropping a bunch of rocks in, But at the same time, like a tsunami changes the whole level of the lake, but that's not like little.
So do we have kind of mapped out like the history sort of the universe?